Hi folks, thanks for tuning in or checking out this video. This is the weekly meeting for 161 for Sam's sections. We'll be talking about 6.3 and an introduction to the area problem, and then answering questions about 6.2 and 6.3 as they come up. So the chapter 6 is about integrals in general, and what you've seen in 6.1 and 6.2 is that when we write an integral, right, using that sort of S-shaped sign, what we mean is find an antiderivative. And 6.3 makes a different meaning, or introduces a second meaning for that notation, which might be annoying at first. You're like, wait a minute, another time in math where they're using the same symbol for more than one thing. Yes, temporarily, taking antiderivatives and finding the area under the curve are different concepts. But what we'll find this week is that actually they're very deeply related via the fundamental theorem of calculus. So I want to talk a little bit about the area problem just to motivate section 6.3 and 6.4. Calculus has, as a whole, has a few very big important ideas. One is the concept of limits. How can we get infinitely close to something? How can we deal with concepts of infinity for a function? So ideas of limits, that's one of the most important ideas about calculus. Then we use limits to talk about derivatives. And when we talk about derivatives, one of the characterizations of the derivatives is the slope of a tangent line to the curve. And what we've seen in the previous chapters is that the slope to the tangent line can also be used to model all sorts of other phenomena as well. The area problem is a third sort of fundamental important idea or question in single variable calculus. And here's what it concerns us with. If we have some curve, right, so some function here, how can we find the area bounded by that curve from one point to another point? So how can we find the area of this shape down here? And we're going to develop some pretty sophisticated tools for doing that, but let's start with some simple examples and ask, what could this area actually tell us? What could it represent? And what I want you to do is imagine that the function that I'm drawing here, f, actually is a velocity function, right? So we have time measured here, and we have the velocity of a car that I'm driving there. So let's say, for example, that my velocity is 80 miles per hour in some positive direction, and then I drive 80 miles an hour for 2 hours. Okay, so if I graph my velocity versus time, my velocity would be constant, right? And so this area here, well, we could calculate the area, right? Here's 1 hour, here's 2 hours. The area here would be 2 hours times 80 miles per hour. And so the area of this rectangle is 160, right? That's just geometry. And if you think about it, though, that area also represents the distance that I've driven, right? This is back to like, not even pre-algebra here. Distance equals rate times time, essentially. And this is an easy problem because my rate is constant and my time is 2 hours. And so really, that 160 miles that I drove, we can think of as the area of that rectangle. Okay, that's pretty easy. So that was where my velocity is constant. All right, well, let's change the problem a little bit. So again, I'm going to use the vertical axis to represent the velocity of a car that I'm driving, and I'm going for a drive for 2 hours. But now let's imagine that my velocity changes over the course of that trip. Let's say I start at a velocity of 60 miles an hour, and then by the time I finish the trip, I'm going 100 miles per hour. Okay, so here is one point, the beginning of the trip, 60 miles an hour. At the end of the trip, 100 miles an hour, and my velocity will vary will vary at a proportional rate between those. Okay, so rate times time should still equal distance, even though my rate of change, my velocity is changing throughout this drive, starts at 60 and goes to 100. But still, that region below the curve should give me the total distance that I've driven, right? And we could try and find that area in a variety of ways. We can subdivide it, right, into different regions. We can use the area of a trapezoid if we want. I find it easiest to just sort of divide this into two different problems. Let's find the area of this rectangle down here and the area of the triangle up here. Well, the rectangle down here has width 2 hours and height 60 miles per hour. And so the area of that rectangle would be 120, and the units associated with it would be hours times miles per hour, which would give me miles. So 120 miles is the area of the rectangle down here, and up here is a triangle whose base is 2 and whose height is the difference between 160. And so the area of that triangle would be 1/2 base times height. So 1/2 times 2 hours times the height of 40 miles per hour. We're getting to the edge of the screen here. And so that area would be 40 miles. And so the area as a whole is again 160 miles. So in both of these drives, I've driven the same distance. In the first case, I did that by driving 80 miles an hour the whole time. The second time, I had constant acceleration, right? So I sped up over the course of the trip, starting at 60, ending at 100, then I traveled the same distance. What we're going to concern ourselves with in the calculus course is a few very simple examples like this, where we can use geometry formulas to help us find the area under the curve. But what we'll be able to do is take more complicated functions, like let's say my velocity function look like this. So again, a 2-hour drive, but now my velocity is a smooth curve, right? So again, the area under the curve, I don't really care what the endpoints are in this example here, but again, the area under that curve would tell me how far I've traveled over the course of those 2 hours. So these are the types of problems that we want to be able to do in calculus. So I gave an example of driving a car. It's a pretty simple example for us to imagine. But here's some other contexts in which we could use a very similar model, or we could use an area model for real-world modeling. Maybe instead of velocity, maybe this is a rate of change showing how some pollutant enters a body of water. We want to know by how much the total has changed over a certain amount of time. Maybe this is some marginal cost function that we're looking at in economics or business, and we want to know by how much our total revenue or profit has changed. All of these problems can be modeled using area functions. So that's just a little bit of motivation of what the area problem is, why we want to find the area beneath the curve. And 16.3 starts to give us a way to approximate the area underneath the curve. And that might be a little bit annoying. I know the times when we have a method for approximating something, we should answer the question like, well, why aren't we just calculating it directly? Don't we have mathematics to do these things directly? Yes, we do. And the reason that we want to approximate it first is twofold. First, sometimes an approximation is good enough and much easier than going through the process of finding the exact area. Secondly, and most importantly, our method for finding something exactly is actually going to involve our approximation method. And so I want to show you graphically what we mean by a Riemann sum. So let's suppose that we have some function f. Again, I'm just drawing it arbitrarily, continuous function here. And we want to find the area beneath the curve between 2 points, A and B. All right, so we want to find the area of this region here. Well, let's talk about some bad and better ways of approximating the area of that green region there. Well, let's see. The height of this point here, if this is the function f of x, or y equals f of x, here are two x values, a and b. The y value right here, that would be f of a. And then over here would be f of b. So here's some bad approximations. So if we really didn't care about getting what this area was, we could just calculate the area of this rectangle right here, right? So what would the area of that rectangle be? It's obviously an overestimate. It would be too big. Well, the width of that rectangle would be b minus a. So there's the width, b minus a. And then the height of that rectangle would just be f of b. Right, that would be a bad approximation. We're saying, all right, that green region, it's pretty much a giant rectangle. Okay, well, that's not a very good way of approximating it. We could also use this left-hand endpoint, right? We could make a rectangle that's exactly this tall. That's also a bad approximation. That would be b minus a. That's the width of the rectangle down here, times the height f of a. Okay, so those are not great approximations. The important question is, given some approximation for that area, how can we make it better? Well, there's a couple ways we can make this better. We could average the two, right? We know that the larger rectangle is too big, the smaller rectangle is too small. We could maybe even like look at the midpoint instead of like the endpoints of this interval. We could like take the middle point, like the average of those two, and go see what the height of the function is. That might be a little bit of a better estimate. But really the best thing that we could do is, instead of using a single rectangle or a single shape to approximate the area, let's use multiple rectangles. I'm just going to start by using two rectangles here. All right, so we're again still trying to find the area of the green region there. If I use two rectangles, well, okay, I'd have to divide this interval from A to B in half. And if I do that, I'm just going to write this in general. I'm going to call that delta x, right? That's like the width of these angles here. Or sorry, the width of these rectangles. And I'm choosing to make both rectangles of equal width. I don't have to do that, but it's usually pretty convenient. So my idea is I'm going to approximate the green area by making two rectangles, each of which has width delta x. And now the height of the rectangles we have some choice over. I'm going to do this two different ways. I'm going to do what we'd call a left-hand approximation using blue. And I'm going to do a right-hand approximation using purple here. When I use a left-hand approximation, so what's our region R? I'll use green here. So the area of our region R is approximately the area of two rectangles. If I use the left-hand endpoints, what I'm going to do is take the left-hand side of each rectangle, go up to the function, and use that for the height. So if I did that, here would be my first rectangle, and then here would be my second rectangle, and we'd add those two things together. Okay, so how would I calculate that? Well, the first rectangle has width delta x, and it has height f of a, right? Because we use the left-hand side of that rectangle to calculate the height following the function. So delta x times f of a. That's rectangle 1. Rectangle 2 also has width delta x. Now its height is the function evaluated at this midpoint right here. So we could write that a couple different ways. It is a plus delta x, right? So a plus delta x would get there, b minus delta x would get there. I'm going to write it as f of a plus delta x, right? So this point right here is just a plus delta x. And its height would be f of a plus delta x. Okay, so what I've done then is I've used two blue rectangles to approximate the area, and that's what we call a left-hand Riemann sum. Let me introduce some notation here. I don't like using R for the region here. I'm going to use, well, let's say this is a left. I'll just use words for now. So this is a left sum, or left Riemann sum, using two rectangles. So our green region is approximated by adding two rectangles in the left using left-hand endpoints. Let's take a look at the right-hand sum. So I could still use two rectangles to approximate this area. If I use the right-hand endpoints, here are the rectangles that I'm talking about. My first rectangle, again in purple, has width delta x. And now we're going to use the right-hand side of that rectangle to generate the height. Right, so here's that first purple rectangle. The second rectangle, I'm going to use the right-hand side, so that's up here. Here's my second right-hand rectangle. Okay, so the blue and the purple are both different approximations of the green region. The blue rectangles are using the left side of each rectangle to generate the height. Purple ones are using the right side of each rectangle to generate the height. And so our right-hand sum with two rectangles. Okay, the first rectangle is with delta x, and its height is actually f of a plus delta x. It's actually the same rectangle that we have here. The second blue one is the same size as the first purple one. So delta x times f of a plus delta x. And then our second rectangle here also has width delta x. And now the height is the right-hand endpoint, so f of b. Okay. Now the idea here is by going from one rectangle to two rectangles, we've made a better approximation of the area. So it's still not a great approximation. If you look at the area of those two blue rectangles, I hope we can agree, it looks like that's an underestimate. It looks like that's not enough area to completely make up the green region in the graph. If we look at the purple rectangles, so we take the area of this purple rectangle and that purple rectangle, I'm not going to draw it in, this is a little bit cluttered as is. That looks like it's an overestimate. That looks like it's more than the green area. And the idea here is that we can make better approximations by making more rectangles. Now the introduction that I've just given here, I haven't defined a function f. This is all using variables, so it's a little bit abstract. I think it'll make a little bit more sense if we take a look at some examples from WebAssign that ask us to approximate area. I did want to pause right here and both welcome people who have joined and see if there are any questions so far. A good way to ask questions along the way without interrupting me is to type them into the chat. You look at the bottom of your screen, there should be a chat window. I'll switch back over here just to say hi. Hi folks, hi Borja, Kristen, a lot of people have joined now. Any questions so far just on my introduction to the area problem or using rectangles to approximate area? Again, like we're going to do a specific example in a minute that should help. Okay, so I'm going to hop into WebAssign and see if I can share some problems from 6.3. Just bear with me for a moment here. Okay, so hopefully you guys are now looking at what I'm looking at, which is the WebAssign problems from 6.3. All right, so I want to look, let's see, I think let's do problem one together here. Problem one is a pretty straightforward function. We can model it, it's a line. We can both approximate the area and find the exact area. Now, I know that your problem one is going to have some different coefficients here. It might be a little bit different. I'm going to copy the function I see here just onto the whiteboard, and we'll pop back and forth between looking at the assignment and looking at the whiteboard here. So our function is 6 minus 2x, and we want to find the region R under the graph from x equals 0 to x equals 3. And we'll do part A without going to the whiteboard here. So thinking about our function, f of x equals 6 minus 2x, that's a line, right? It's a line of slope -2 and y-intercept 6. So let's see if we can find that function amongst the ones here. The y-intercept here looks like it's more than 6. Y-intercept in the second graph looks like it is 6. In fact, that's the only one that has y-intercept 6. Let's just confirm that the slope is indeed -2. I can see that over the interval from 0 to 3, the y values decrease from 6 to 0. And so my rise would be -6, my run would be 3. -6 divided by 3 would be -2. And so I feel pretty good that this second function here is the one we want. And so what we're going to do in part B, C, and D is we're going to both find the exact area of the region there, and then we're going to use some Riemann sums to also approximate the area, okay? And I think this is a good introduction to both using Riemann sums and using geometry formulas. So I'm going to bounce back and forth. Let me just copy our parts here. So part A, we want the exact area. I'm just writing these on the whiteboard so we don't have to change too often. Part B, we want a Riemann sum. By the way, a Riemann sum just means adding a certain number of pieces of area together to approximate the area under the curve. We can use a variety of shapes, but we usually use rectangles. So what do they want there? Riemann sum with 4 subintervals, or 4 equal subintervals. And what else do they want? Choose representative points to be the left endpoints. All right, that should probably fill up our whiteboard. So I'm going to switch back over to the camera. Stop the sharing. Okay, and hopefully you guys are looking at my whiteboard here. Let's see. For folks who joined, yeah, it looks like everyone's muted. That's great. Okay, so here is our function. We want the exact area, and then we want to Riemann sum using 4 intervals with a left endpoint. So let me copy that function over here. So we had y-intercept 6, so 1, 2, 3, 4, 5, 6. And then our interval was from 0 to 3. And so our function was just this line segment. And the region that we're looking for is right here. Okay, so some of these problems are pretty easy to do using geometry. So the exact area of R is a triangle, right? So we can use the formula 1/2 base times height. The base is 3, the height is 6. So 1/2 times 3 times 6 is 9 units squared. So the exact area of this region is 9. We just know that from geometry. All right, so the Riemann sum is an approximation, and they've asked us to do this using 4 subintervals. So let's see. So our interval spans 3 units, and we need to now divide that 3 units, or that interval of 3, into 4 equal subintervals. Let me draw what that looks like, and then we can figure out what these values are. So again, I'll just color code what I'm doing here. We're going to use the left-hand side of each one of these rectangles to calculate the height. So here's our first rectangle. Here's our second rectangle. Here's our third rectangle. And here's our fourth rectangle. And so our idea is that we can approximate the region in that underneath the curve by adding these 4 rectangles together. It's a little bit of a silly example because we already know the exact area, but what this problem is showing is that as we increase the number of rectangles, our approximation gets better. And that's going to be really important for the next section when we develop a calculus tool to find the exact area underneath the curve. Okay, so the interval, the full interval goes from 0 to 3, right? And so delta x in this case, right, that's the width of each rectangle, is going to be, since there are 4 subintervals and the total length is 3, we'll take that total length of 3 and divide it into 4 subintervals, right? And so we're saying we got delta x, delta x, delta x, delta x. That's a constant width of those rectangles. All right, well, let's calculate the height of each one of these rectangles. And by the way, I'm going to call this, we'll call that R1, R2, R3, and this one will be R4. Okay, so what we want to do is we want to add those 4 areas together. Well, what's the area of R1? So if we want R1 plus R2 plus R3 plus R4, the 4 rectangles, well, R1 has width delta x, so the width would be 3/4. And the height of that rectangle, well, the height would be whatever the height of the line is when x equals 0. So f of 0. So 3/4 times f of 0, right? That would be the area of the first one. I'm not gonna figure out what this is exactly for another minute. I want to write this out first. The width of my second rectangle is also delta x, so it's also 3/4 times the height of the second rectangle. Okay. Well, the height of the second rectangle, you know that right here is the point 3/4, or right, that's our x value, right? And we decide delta x is 3/4. So the height of my function then would be f of 3/4. So we're going to x equals 3/4, and we're looking up to find the function and see how tall that rectangle is. Hopefully that makes sense. Okay, what's our next endpoint? Well, delta x is 3/4, so I've gone 3/4. I go another 3/4, so now I'm at 3/4 plus 3/4. It's 1.5, or if you prefer, 3/2. All right, so my next rectangle has width 3/4 and has height f of 3/2. Right, that's the left side of my third rectangle plugged into the function. All right, so my fourth rectangle also has width 3/4, and it has height f of whatever this point is here. Well, let's see. We've gone 3/4 plus another 3/4 plus another 3/4. That would be 9/4. So f of 9/4. All right, I want to pause here and just make sure we understand where all these things came from. The delta x, that's the width of each rectangle here, is 3/4. So there are 4 rectangles, they all have width 3/4. The f of 0, f of 3/4, f of 3/2, f of 9/4, where did those numbers come from? Well, 0 is the left-hand x value of the first rectangle. 3/4 is the left-hand x value of the second rectangle. 3/2 is the left-hand x value of the third rectangle, and 9/4 is the left-hand side of the fourth rectangle. So what we have here is the sum of 4 rectangles, and we're going to get some actual numbers for this. I got a question in the sidebar. Are we using 4 rectangles because the problem tells us to? Yes, we are. And in general, we're almost always going to use rectangles. In fact, I think all the problems that we ask you to do involve rectangles. It's a great question, by the way. One thing that you can do, we're not going to do a lot of problems like this, but instead of using rectangles, we could use trapezoids. We could connect these 2 points using a straight line. And that makes our geometry like a little bit more complicated, and it gives us a little bit better of an approximation. But the main way that we're going to make better approximations is not by changing the shapes that we use, but by using more rectangles. All right, so great question. All right, and I want to show like one more thing here. Because we chose each one of these rectangles to have the same width, I could actually also kind of like rewrite this in a simplified form. Since all these rectangles have width 3/4, I could just factor out that 3/4 and calculate f of 0 plus f of 3/4 plus f of 6/2 plus f of, sorry, not 6/2, what do we have there? We have f of 3/2. And then f of 9/4. So if we just want to save on our multiplication, we can factor out that 3/4. And let's actually calculate that now. So I got my 3/4, and let's evaluate our function at all these different points. F of 0, so f of 0, again, notice this is the very top of the screen, f of 0 would be 6 minus 2 times 0, so f of 0 is 6. And sometimes we can just look it up on the graph, like I can see what the y value is, it's exactly 6. So here's my first y value. Second y value, I want to know this height right here. Well, maybe it's worth me actually plugging into the function. I'll just do this over on the side here and we can clean up. So what is f of 3/4? Okay, so I'm just using the function that's defined up here. F of 3/4 is 6 minus 2 times x. So 6 minus 2 times 3/4. I know fractions for some people are probably the hardest part of these problems here. I don't want to spend a ton of time on converting fractions, but I'm happy to go back and take a look at this later if people have questions about how I did this. 2 times 3/4 is 3/2, right? Because 2 is just 2/1. And so what I'm going to do is rewrite 6 as 12/2 so that I can subtract with a common denominator. So 12/2 minus 3/2 is 9/2. Right, so that's the height of my second rectangle. Okay, so on to the height of my third rectangle. So my third rectangle, if we use that left-hand endpoint, here's the height of the function. Well, also notice that this is the exact midpoint of the line, right? And the y values started at 6 and went down to 0. So at the midpoint, the y value will be exactly half of that change. So the y value is going to be exactly 3 here. If you'd like, you can confirm this by plugging in 3/2 into our function. I'll just do that. That's not too bad. F of 3/2 is 6 minus 2 times our x value 3/2. and I'm on the very edge of the screen here, sorry. So 2 times 3 halves is 3, and 6 minus 3 is 3. Apologies, slide that over there. All right. So first y value, second y value, third y value, and our last y value is going to be the left-hand side of this fourth rectangle here. And so that would be f of 9/4. So f of 9/4 is 6 minus 2 times our x value, 9/4. And that's 6 minus 9 halves. Again, we've done this already. We know that 6 is 12 halves. So 12 halves minus 9 halves would be 3 halves. Okay. So now what we have here is the area of 4 rectangles added together. I'm going to erase in a moment. We'll actually do that calculation there. But what's most important is just this idea that we're approximating area by doing a finite number of rectangle calculations. Even if the function f was like a lot more complicated, if it wasn't a line, we could still plug in these x values and find y values. All right, so that's going to be the same no matter what the problem is. I'm going to erase a little bit of the work that I did to evaluate the function at different points, just so we can continue this calculation and come up with an approximation for our area. Okay, so again, we're still trying to do that Riemann sum approximation using 4 subintervals of equal length. I have it written out like this, and I'm going to finish the problem. My recommendation, I know not everyone loves fractions. My recommendation, because of how much multiplication is going on, is to use fractions instead of decimals, and definitely not to use mixed numbers. Mixed numbers are difficult to work with. Fractions are very easy to multiply and divide. Decimals are not so easy to multiply and divide. So I do all these problems using fractions because there's so many area calculations involving multiplication. So we'll take this up here and continue. So first I want to add all these quantities inside the parentheses. So I'm going to convert that into fractions over 2. So 6 is 12 over 2. Add that to 9 over 2. 3 is 6 over 2. And then finally, add that to 3 over 2. All right, so how many halves do we have here? 12 plus 9 is 21, plus 6 is 27, plus 3 is 30. So 30 over 2. So we have 3/4 times 30 over 2. And I can do some simplifying here. If I divide 30 by 2, that's the same as 15 over 1. And so 3 times 15 is 45, and 4 times 1 is 4. So here is our approximation for the area. Well, like, what is that? 45 over 5. Well, 40 over 5 would be 10, and 45 over 4 is close to 44 over 4, which is 11. All right, so as a mixed number, this is 11 and 1/4. So that's our approximation, is the area is about 11 and 1/4. We know that the actual area is 9. So this is like an okay approximation. It really would depend on the context of the problem. There's no set rule for what's a good approximation and what's a bad approximation. It should not surprise us that our approximation is more than the total, because each one of these rectangles is bigger than the region underneath the function f. Oh, sorry, crazy traffic outside. So this is an overestimate. I'm not going to go through and do a right-hand estimate, but if we use the right-hand side of the rectangles, our first height would be here, second height would be here, third height would be here, and our fourth height would be 0, and that would be an underestimate. Okay, so let's see where we are in the problem. We've now found the exact area underneath the curve. We've used 4 subintervals to approximate the area, and we got 11 times 1/4. Let me go back to WebAssign here, and we can take a look at the rest of the problem. Okay, so the rest of the problem here, they want us to repeat part B with 8 subintervals of equal length. This is really weird. I think this actually might be a glitch. If we're using 8 subintervals, n is not equal to 10, n is equal to 8. Huh, that's really weird. All right, so let's go back to the whiteboard. And I don't think I'm gonna show all the calculations here just because we don't need to do 8 fraction multiplication and addition problems together. But I do wanna show you what that would be graphically if we move to 8 subintervals. So let me stop on the screen sharing here. I'll go back to the whiteboard and then we'll wrap this problem up. So if I wanted to do 8 subintervals instead of 4, what I would do is I take delta x and actually make it even smaller, right? So 1, 2, 3, 4, 5, 6, 7, 8. If we think that this part up here, right, that's the error, and this is the error, and this is the error, and this is the error in our approximation, if we go to 8 subintervals, and apologies, I know we're kind of running out of resolution here in this drawing. I'm just going to do it for region 1. If I split this into 2 more rectangles, look at how that error decreases. Before it was this whole region, this whole bigger triangle above the curve. That was how much our approximation differed from the actual value. By making more rectangles, now our error is a lot smaller. It's just these 2 smaller triangles. And the important thing to see here is that as we add more rectangles, the error decreases and our approximation gets closer to the actual area beneath the curve. Okay, so I want to pause here and see if there are questions so far. Thank you for folks who have typed into the chat. I see 1 question so far. I'm going to pause recording too, just for a moment. Okay, so seeing no problem or no questions on this problem, I'm going to let this go. And we're going to take a look at another function. I think I'm going to try and draw this one a little bit bigger so we don't run out of space on this whiteboard here. All right. So let's see. Okay, so by the way, in problem 2, this one shows this process here. Right? They show a variety of rectangles. Boy, that hover text is annoying. So they show some rectangles here. And one thing that's interesting about problem 2 is to calculate the height of each rectangle, they haven't used the left side or the right side of the rectangle. They've used the midpoint. All right, and that would be one way to improve the accuracy of our approximation as well. It's a little bit interesting, but mainly the technique we're going to use, rather than using different heights or using different shapes, is to just add a whole bunch of rectangles instead. All right, so let's take a look at, yeah, we can look at problem 4. Oh, this is nice. There's only 4 problems on this WebAssign. You lucky people. All right, so problem 4 gives us a different function. So f of x equals x squared plus 4. And we want to find an approximation of the area of the region R under the graph of the function 0 to 2 using 5 subintervals. Okay, I'm going to change this a little bit because I can't do all the problems for you. I know these WebAssign problems are going to count for an exam grade, so I'm not going to do the exact problem. I'm going to do a similar problem. Let's take f of x equals x squared. I'm going to make it x squared plus 1, and I'm going to do 4 subintervals. And I'm going to draw it, and we'll do the calculations as well. And for this one, let's use right endpoints. So I'm not doing exactly problem 2, but I am going to do one that's pretty similar to it. Okay. So f of x equals x squared plus 1. We're going to approximate the area using 4 subintervals. We're going to use the right-hand side of each subinterval for an endpoint, and we're going to use rectangles. I'm pretty sure every problem that we do in this section, we're going to be using rectangles. All right, so what does this function look like? Well, we know that y equals x squared is an upward opening parabola centered at the origin. And so x squared plus 1 is that same shape, just shifted up by 1 unit. Oh, I need one more piece here. I need the interval, right? I need to know what values of x I'm going to take a look at. So let's say the interval from 0 to 2. All right, so 4 subintervals of equal width. Our function is f of x equals x squared plus 1. And here is the graph, right, upward opening parabola, like that. and the region that we're trying to find is under the curve from 0 to 2. Okay, so let's just do a little bit of drawing first, and we'll try and set up this Riemann sum. So my interval, the full width of the region is 2. The subintervals, there's 4 of them, so we're going to divide that interval into 4 equal pieces. So 1, 2, 3, 4, those are our 4 subintervals. And that's a sequence of x values. So let's say the following. Let's say our first x value, that's x1. And here's x2. And here's x3. Oh, no, I said right-hand endpoints. Sorry, guys. So if I'm using right-hand endpoints, my first x value would be there. That's the right-hand side of the first subinterval. Right-hand side of the second subinterval, right-hand side of the third subinterval, and right-hand side of the fourth subinterval. Okay, so x sub 1 would be 1/2. X sub 2, second x value is 1. X sub 3 is 1.5, so 3/2. And x sub 4 is 2. All right, so what I've done is I've taken my interval from 0 to 2 and I've divided it into 4 equal subintervals, and I found the right-hand endpoint. If you want to think about a more generalized way to do this, if our interval goes from a to b, then our delta x would be b minus a. So b minus a is the entire interval divided by however many subintervals we want, right? So that change in x is the total interval length divided by however many subintervals we want. And, right, delta x in each one of these cases, well, the entire interval is 2. We divide it into 4 pieces. So in this case, delta x would be 2 divided by 4, so 1/2. So let's set up our Riemann sum here. So our Riemann sum using 4 intervals is going to be the following rectangles. First rectangle starts at 0 and goes to x sub 1, and its height is using the right-hand value. So I take that first x value and I plug it into the function. Function says this is the height. Second x value, plug it into the function. There's the height. There's my second rectangle. Third x value, plug it into the function. All right, there's my third rectangle. And here is my fourth rectangle. So we're going to add those 4 rectangles together. By the way, I think we can also see that this Riemann sum is going to overestimate the area. The area beneath the curve is actually, right, the space underneath, and we're going to overestimate by these small area pieces up there. Okay, so our area is going to be approximately, not equal to, but approximately equal to these 4 rectangles. Well, each rectangle has width delta x, right? And we're using 4 different heights to calculate each one of those rectangles. The first one is f of x1, right? That's the height of the first rectangle. And then f of x2, and f of x3, and here, f of x4. Right? So our area is made up of 4 rectangles. They all have the same width. They have different heights. The heights are given by our function evaluated at these x values. All right, let's do some actual numbers here. Delta x is 1/2, right? That's the width of each one of these rectangles. What's f of x1? Well, f of x1 is 1/2. So f of 1/2 would be 1/2 squared minus 1, right? I've just plugged that x value into, plus 1, into our original function. And so 1/2 squared is 1/4. 1/4 plus 1 is 5/4. All right, again, I know there's some extra fraction steps here. I'm recording this. If you want to go back and pause this or do this work on your own, where these fractions came from, I'd encourage you to do that. I want to move quickly through this in case there's questions about other problems as well. All right, well, what's f of x2? F of x2, that's f of 1. So 1 squared plus 1 is 2. What's f of x3? F of x3 is f of 3/2. And so that's 3/2 squared plus 1. 3/2 squared is 9/4 plus 1, which is 4/4, gives us 13 over 4. Sorry, I'm going to slide this up a little. There we go. Okay, so f of x4, that's f of 2, is 2 squared plus 1, so 5. All right, and so our Riemann sum then is that constant width 1/2 that's present in all 4 rectangles times the sum of these 4 heights. Now, knowing that I'm going to have to add these things together, when I copy that over here, I'm going to write them all as fractions over 4. So first height is 5 over 4. Second height is 2. If we write 2 as a fraction over 4, that'd be 8/4. Third height is 13/4. And our last height is 5, which is 20/4. Okay, so now let's add these things together. Yeah, that's right. 5 plus 8 is 13. 13 plus 13 is 26. And 26 plus 20 is 46. So we have 1/2 times 46 over 4. I can do a little bit of simplifying before I multiply. I can divide a 2 from the numerator and the denominator, and that gives me 23 over 4. I divided 46 by 2 and divided 2 by 2 gives me 23 over 4. Right, and that's my final answer. That's my approximation for the area underneath the curve. So I'll give you a preview into what we're doing in 6.4 if you haven't taken a look there yet. We can see that we get better approximations by making more rectangles. I could give you a ton of problems where you do like 5 rectangles and then 10 and then 20 and then 100. There'd be a lot of calculations. What would be ideal is if we could use infinitely many rectangles, right? If only we had a tool for dealing with infinite quantities. Well, guess what? We do, and it's called limits. In 6.4, we're going to explore how we can use limits to give an exact calculation of the area underneath a curve like this. So I wanted to pause here and see if there's any questions. This is all I wanted to do to introduce 6.3. So if people have questions about problems from 6.2, I'd be happy to go back there. Would anyone have questions about this or want to chime in on where we should go next? And again, you can either unmute yourself. By the way, if you're muted and you want to speak, if you hold down the space bar, it will temporarily unmute you. You can also type into the chat if you guys have suggestions of things you'd like to look at. So one suggestion I was going to make, if you're working on your quiz and are having some trouble with any of the use substitution problems, the video that I recorded on Thursday has several use substitution problems in it that might be helpful to take a look at. My other commentary on integration by substitution is really what we're looking for is we're trying to run the chain rule backwards. So we're looking for some function and its derivative within the problem that we've been given. If we can identify those things, the problem becomes really easy. And so one of the things that I'm always on the lookout for is, can I find some function and its derivative inside a problem? I don't want to quite erase this yet, but I do want to show you what I'm talking about in 6.2, just in case you guys have questions about that. I'm going to switch over to, let's see if I can find the right one. Here we go. Okay, so I just want to take a look at a couple of these like later problems in WebAssign. This assignment has already been due. I think we're past the extension date, so it's fine for us to take a look at it. I was looking at problem 17 in particular. I thought this was a nice one to maybe look at. So problem 17, we're looking to see if there's a choice of u that we can turn this complicated looking antiderivative into a simple one. And one of the things that I noticed is that I have x to the third power in the denominator and I have x to the second power in the numerator. And I know that when we differentiate powers of x, it decreases our power by 1. And so the thought I have here is like maybe we can take this problem and we can rewrite it using a substitution for that cubic equation there. So I'm going to copy this onto the whiteboard. We'll take a look and then go from there. By the way, thank you guys for tuning in. Like, feel free to stop at any point when it becomes less relevant for you. Also, feel free to interrupt if there is something else you guys would like to look at or other questions that you have. All right, so I'll pop over to the whiteboard again here. Okay, so cool. All right, I'm gonna erase the last of that, rerun some problems. We can take a look at this use substitution. We'll probably call it quits after that. All right, so the question is, can we turn this somehow into an easier problem? Because this is just not a function whose antiderivative you're supposed to know. Like, I don't know it. No one really knows it. You might be able to think through it in your head. That's possible. But no one just like looks at that and recognizes like where that came from. So the idea is if we can simplify this somehow by choosing the right value for u, we can turn it into a much nicer problem. So like I said, I noticed that I have a degree 3 polynomial in the denominator and a degree 1 polynomial in the numerator. So I'm going to try something. I'm going to try letting u equal the denominator. And my emphasis is on trying because especially when you first start doing these things, you're going to not always make the best choice. You're going to choose the wrong thing for you, and it won't help. You might be frustrated, but like that's okay. That's pretty normal when you start these things. If we pick the right value for u, this antiderivative is going to become a lot easier. So let's try this. Let's try u equals x cubed minus 12x plus 5. Okay, so we're looking for u, and we're also looking for the derivative of u du. So if my u is x cubed minus 12x plus 5, then du would be 3x squared minus 12 times times dx. All right, so all I did is I took my derivative of my choice of u. This is the point where I zoom out from it and say, okay, do I have this thing? Do I have u and du somewhere in the problem? Or can I make these things appear? In the first problems in 6.2, if you make the right choice of u, you will find du exactly in the problem. In the later problems, and probably some of the ones you're seeing on the quiz, we might not have exactly du, but we have something very close to du. So if I go back and look at what I have, okay, so there's my u in the denominator. And in the numerator, I don't have 3x squared minus 12 dx. I have x squared minus 4 dx. If we start comparing what we have to what we want, what we might notice is that what we have times 3 equals what we want. Like I wish I had 3x squared minus 12. I have x squared minus 4. I want to show you a trick for this problem. And I really like solving these problems this method. This is not the only way to do it. In the course videos, you might see a different technique. But one thing that we can do, we know that derivatives and antiderivatives have a constant multiple rule. So if I multiply by some number on the inside or on the outside, it doesn't matter if I multiply on the inside or the outside. So here's the trick that I'm going to do. I'm gonna kind of like hack our original problem. And here's how I'm going to hack it. I'm going to multiply what we have here by 3 inside the integral. Now, normally that wouldn't be allowed, right? That would change the problem to a new problem. But if I also multiply by 1/3, if I multiply by 1/3 and I multiply by 3, I haven't really done anything. Those things cancel each other out, right? Those are inverse operations. But look what effect that has on my integral. If I multiply by 3 on the inside, then what I have is 3x squared minus 12 dx, which is exactly what I want to do this u substitution, right? So I'm hacking the problem to make an equivalent integral that's in exactly the form that we want here. All right, so let me finish that. If I do that, then I can rewrite my difficult integral as an easier one. So what I would have then is 1/3, right, because I have a 1/3 out in front, times the integral of this thing. Now I'm going to rewrite this integral in terms of u. So what do I have down here? I have 1 over u, right, so I have a u in the denominator. And then 3 times x squared minus 4 using distribution is 3x squared minus 12 times dx. So that is exactly our expression for du. Now, even if it was sort of magic, even if you're like, I'm not sure that I'd know to choose that for you, what I hope you can see is that this choice for you changes from a really complicated looking antiderivative into actually a really simple one, right? du over u, that's a known derivative, right? The derivative of 1 over x, sorry, the derivative of ln x is 1 over x. So the antiderivative of 1 over u du would be natural log u. So I'll finish the problem now. So our integral then is 1/3 times the natural log of u. And I'm going to do one more thing here. It's important when we do this for antiderivatives. The natural log function won't accept 0 or negative values as entries. And so when we take that antiderivative, one thing we'll do to make sure that we never have negative answers is say absolute value of u plus c. Okay? Now the last step, I introduced this variable u just to help me along the way. It's important, a couple notational things here. Whenever I take my antiderivative, two things happen. The differentials go away and the integral goes away. We've taken the antiderivative, and so we add the plus c at this point. This is where we no longer have an antiderivative to evaluate. We found the antiderivative. If you don't add that plus c, you'll get at most 3 out of 4 points. If you don't change this back to x at the end of the problem, you'll also get at most 3 out of 4 points. So my last step now is to rewrite the whole thing with x. I'm just going to change that u back to x cubed minus 12x plus 5. Okay, so this is a complete problem using u substitution or variable substitution to solve an indefinite integral. I'm going to pause here and see if folks have any questions. We'll just have like a little bit more commentary and then we'll wrap it up here. So I use this technique of changing my integral into what I wanted it to be. So I wanted 3 times x squared minus 4. I wanted that 3x squared minus 12. So I multiplied by 3 and I divided by 3. One inside the integral and one outside the integral. The other way to do this problem, if you don't like that, or if the other videos appeal to you a little bit more, the other thing that we could have done with this expression right here is if we divide both sides by 3. If we take this expression, divide both sides by 3, we would get x squared minus 4. Right, that's our expression here, divided by 3 times dx equals 1/3 du. Now, if we did that, we could have just directly substituted 1/3 du for the x squared minus 4 times dx. It gets us to the exact same place. I prefer doing it the way I illustrated in pink. Okay, I see a question. When will the next Zoom call be? So I'm going to, on Thursday, same time, so Thursday at 11:30. I'm going to do the same thing. It should be the exact same link, by the way, to connect to that meeting. I've made those standardized for the 2 online live sessions that we have. And I think I'm going to focus more on 6.4 at that point. And then any other questions that folks have. Okay, anything else, folks? Well, thank you for joining. I hope you're well wherever you are. If you're in much different time zones and it's difficult to meet during the office hours that I have proposed, I have a student who's in Australia. I have other students who are in different parts of the country and the world. Feel free to shoot me an email. I'm up pretty late most of the time, so I'd be happy to schedule a meeting outside of the scheduled office hours if you'd like. I hope you guys are well. I hope your courses are going well. If you have any sort of feedback for what we're doing in the course, ideas from other courses, things to avoid that you've seen, and the other online transitions, I'm definitely always interested to hear those things. So let me know, shoot me an email. And I hope, Borja's in Spain. Everything works. I'm glad to hear that. Yeah, feel free to reach out. And thank you guys for tuning in. That's all I got. Take care. Be healthy.